Welcome students to GDC classes. I am Ketki and today we are going to see about pharmaceutical session. In that we are going to see about aerosols. So we are going to see about some of the contents of aerosol topic. So let's see what are the points that we are going to cover in today's session. So first is introduction. We will see what is aerosols. Basically these are pressurized dosage form. What is the mechanism? We'll see how it works. Then we'll see some of the advantages and disadvantages. Then there are different types of medicated aerosols like nebulizer, meter dose inhalers, and we are going to see how it works. Afterwards, we are going to see some of the components of aerosol package. What are the different components, how it is made up of, that we are going to see. Then we are see containers of aerosol package, manufacturing and evaluation of aerosols. So as it is important to evaluate, like we have seen for capsule, tablets, different evaluation parameters are there. Similarly for aerosols also different evaluation parameters are there. So let's start with the introduction first. So aerosols are pressurized dosage form, means some external pressure has been applied and filled into these containers, hence it is known as pressurized dosage form. So it may contain one or more active medicament. Okay, one or more active medicament means active pharmaceutical ingredients which upon actuation is nothing but the process of pressing the nozzle which emits the content from the container. You might have seen some analgesic sprays. So these sprays are nothing but aerosols only. So whenever you will press the nozzle, the spray in the form of spray, it will come out. So that process is known as actuation. So it emits the contents from the container. Next is aerosols are used for topical administration of treatment of burns, minor cuts, infection, various dermatological preparation. Just now we have discussed about the analgesic spray. So these are the topical formulations. So these are used for the dermatological, for burns or for minor cuts, infection. For those purposes, these aerosols are used. Next, very important is the size, the particle size of these aerosols material. So the size of solid particles or liquid droplets in aerosols is normally ranges from, remember this, 1 to 10 micrometer. 1 to 10 micrometer, generally the particle size will range. And it is expressed as the aerodynamic diameter. It is expressed as aerodynamic diameter. So it is represented as d aerodynamic is equal to rho into half d. Rho is nothing but density. Rho is nothing but density of the particle and d is the observed diameter. D is the observed diameter. Remember the range, particle size range, it is 1 to 10 micrometer. Next is a little bit history we'll see, that is first aerosol insecticide. First aerosol insecticide was developed by Goodhue and Sullivan. Goodhue and Sullivan, these were the scientists. They developed the first aerosol insecticide in the US Department of Agriculture. So this was the history and some of the introduction of aerosol. Now let's see the diagram of the aerosol. So basically this is the diagram of the aerosol. So here you can see it is inside a liquefied gas aerosol can. So inside this gas is present which is under very high pressure, it is converted into liquid. Under this pressurized dosage form, it is in the liquid state. So here it is a liquid gas, or it is a propellant mixture also. Whenever you will press this nozzle, whenever this nozzle you will press, the gas will, the liquid will come outside. The liquid will come outside, and you know the atmospheric pressure is less. The atmospheric pressure is less, because of which the liquid will convert into gaseous droplets. Because inside the pressure is high, it is in the liquefied state, liquefied gas, but when you will press the nozzle, the atmospheric pressure is less, it will convert into gaseous form. So that is the reason whenever you will spray something, for example analgesic spray, inside it is liquefied, whenever it will come outside it will be in the form of droplets. So how it will come out? It will come out with the help of dip tube. It will come out with the help of dip tube. Now this is nothing but a seal. It will prevent from coming out. It is a seal. And here it is a nozzle from which the actuation takes place. So this is the diagram. Now let's see advantages and disadvantages. Advantages is rapid onset of action. Unlike oral dosage form, which has to go inside the body of the patient, disintegration, dissolution, various steps are there, and afterwards it will go into your blood circulation. So the action takes some time. But unlike these dosage form, whenever you will spray something, it will directly get absorbed into blood circulation. Hence, the action is very fast. So rapid onset of action. Next is circumvent first pass effect. You know, some drugs undergoes hepatic first pass metabolism, because of which before reaching into blood circulation it undergoes extent of metabolism. So in this case, in the aerosol preparation, there is no liver metabolism, there is no first pass effect, and there is no degradation in the GI tract. Directly the drug gets absorbed into your blood circulation or systemic circulation. Now lower dosage, that will minimize the adverse reaction. Since it is not undergoing any of the hepatic metabolism, the dose will be less. Now the dose is less means the associated adverse effect will also be less. Next is container valve closure are tamper proof. Tamper proof means you will come to know if it is opened or not. So they are tamper proof. Next is along with advantages, some are disadvantages also. So first is expensive. Unlike tablets which consist of only blister and strip packaging, these containers require some specialized, means these dosage form requires some specialized containers. You cannot use any plastic or like aluminum, steel, stainless steel or some other containers are there which can be used. Because why they have to use? Because they have to withstand higher amount of pressure. We are going to see what is the pressure limit and all, but these containers, they have to withstand that much amount of pressure. If pressure is not maintained, then it will not be a liquefied gas. To maintain that liquefied gas in the container has to be specialized one. So that makes it expensive. Next is CFC degrade ozone layer. We are going to see what are the propellants, different propellants. So among that, one is chlorofluorocarbon. So whenever we are using this ozone layer, which is responsible for protecting the earth, our mother earth, with the from the sunlight. So means the harmful radiation will not reach the earth, but this CFC, they degrades the ozone layer. Ozone is O3. So that is the disadvantage. Next is sometimes toxic or irritant. Since we are using it as dermatological, it can become irritate. It can give some irritation to the skin. So that is the disadvantage. And disposal of container is difficult. Definitely, if specialized containers we are using, then their disposal is also difficult. So these were some of the disadvantages. Now let's see with the types of medicated aerosols. So very first is dry powder inhalers. Let me show you the diagram. So this is a dry powder inhaler. First of all, this is taken by the oral cavity. So this is taken by the oral cavity. First say this one. In this is the cross-sectional longitudinal section of that one. So here are the piercing buttons. First of all, here are the piercing button. Inside this, capsule is placed. Inside this, like this, capsule will be there. In the capsule, you will place some diluent along with your active pharmaceutical ingredient. Whenever the patient will press the piercing buttons, these are known as piercing buttons, the capsule will be broken down. The capsule will be ruptured. It will be broken down. After which, because of inhalation and exhalation process of the patient, this capsule will rotate. The empty capsule will rotate, and because of the inhalation process, whatever the material is there, it will go inside the patient's mouth. So here it is written as mouthpiece. So here you can see how the patient is taking dry powder inhalers. Hence, it is known as dry powder inhalers because active pharmaceutical ingredient is present in the dry form. Now here some filters are there. Here you can see some filter are there. Why that filter? Because this will not allow the, now see, capsule has been ruptured, so that capsule shell material should not go inside the mouthpiece. That is the reason these filters are there, so that only your active ingredient and the diluents will go inside the patient mouth. So this is the longitudinal section. This you can see the actual how it looks. These aqua blue color, these are the piercing buttons. Okay, these are the piercing buttons, and inside this space you can see that is of a capsule, where the capsule will be placed, once the patient press the piercing button, the capsule ruptures, and because of inhalation exhalation process, the fluidity, because of that fluidity, it will go inside the patient's mouth. So see here, drug is inhaled as fine particles. So drug is either preloaded in an inhalation device or filled into hard gelatin capsule or foil blister disc. Sometimes it is filled as it is, or it is placed into a disc or capsule. Now lactose, very important. Which of the following is used in to reduce the agglomeration of particles? Now since we are using dry powder, there are chances like some agglomeration may happen. So to avoid that, we are using lactose. So very important, remember this one, lactose. It is used to reduce the agglomeration of small drug particles, and it facilitates fluidization, means taking into the patient's mouth during the inhalation process. So this was about the dry powder inhaler. Next is nebulizer. So basically, let me show you the diagram. So this is a nebulizer. This is a nebulizer. You might have seen in hospitals, especially for children. So the active ingredient is present in the aqueous form, and it goes to the patient's mouth. Like this is a face mask covering your nose and the mouth also. So the active ingredient will go in the steam form. So it is the aqueous preparation. Now see, drug is dissolved or suspended or in aqueous phase and inhaled by the patient through face mask. It produces an aqueous spray this aqueous spray consists of active ingredient and the excipients which are inhaled by patients through face mask. So that is a nebulizer or atomizer. Next is metered dose inhaler. The name itself suggests metered means the dose is already predetermined. The dose is already predetermined. So mostly used to deliver suspension aerosol. Drug is dissolved or suspended in non-aqueous propellant. Remember, for nebulizer it was aqueous. For metered dose inhaler it is a non-aqueous propellant, and it is packed in specially designed pressurized container fitted with metered valve. Specialized container which is fitted with metered valve, and hence it is known as metered dose inhalers, MDI. Predetermined dose is ejected on actuation. For example, sometimes very potent drugs are there. So instead of 5 mg, 6 mg you cannot take. So exact amount of dose is required. So in that case, we are using meter dose inhaler. Next is skin spray. So generally used for local effects. For example, we have already discussed coolants, anesthetic, analgesic. So these are different spray. Next is dental spray. So generally used for local analgesic or anesthetic action. So dry powder inhalers, nebulizer and meter dose inhaler. So here you can see meter dose inhaler. This is a canister, this is a plastic holder, and here you can see is a metering valve. So here it is a metering valve, and this is a mouthpiece, means from here it will go. So propellant with drug suspension, we have discussed, it is for a suspension one, meter dose inhaler. So through here the aerosol will go into the patient mouth. So these are different types of medicated aerosols that we have seen. Now we will see only types of aerosols. So based on what kind of liquid or gas or any other material is present, it is divided into two types. So first is two-phase system. Now what do you mean by phase? something which is separate. For example, gas and liquid. Gas is a different phase and liquid is a different phase. These are two different phases. So it is known as two-phase system. It is known as two-phase system. So it consists of a solution of, active ingredients in liquefied propellant and the vaporized propellant. So it consists of active ingredient in liquefied and the vaporized propellant. So gas is there and liquid. Gas is nothing but solution of active ingredients. Okay. Next is three-phase system. Now what do you mean by three-phase? First is gas, second is liquid, and solid or liquid. Okay. So first gas is confirmed, next is liquid is confirmed, third can be solid or liquid. Third can be solid or liquid. Now gas is there, consists of suspension. If it is suspension, then solid and liquid will be present. So this becomes your three-phase system. In case of suspension, gas, solid and liquid. Now they have said for emulsion also. In case of emulsion, it can be gas, then liquid and this liquid. So gas, liquid, liquid for emulsion. Gas, solid, liquid for suspension. So this becomes your three-phase system and two-phase system. It also consists of active ingredient and vaporized propellants. Since propellants are vaporized, means they are present in the gaseous form. So these are the types of aerosols. Now let's see what are the components of aerosol package. Basically there is propellant. Propellant gives the necessary pressure which is required. It also acts as a diluent material. Next is the container, how it is made up of. We are going to see valve and actuator, how the product will come out, and the product concentrate. Product concentrate is nothing but your active pharmaceutical ingredient or the mixture. Now see, product concentrate. It consists of ingredients or mixture of active ingredients with other additives like solvents or antioxidants and surfactants. So this all terminologies is known as product concentrate. Next is propellants. Propellants we have discussed. It is to produce the pressure. It gives some pressure to expel the medicament. Whenever you will press the nozzle, certain pressure is required so that the active medicament will come out. So this necessary pressure is given by propellant. A propellant has a pressure greater than atmospheric pressure. Very important, remember, propellant, since it is inside the container, it is having higher pressure than the atmospheric pressure at 40 degrees Celsius. They may ask you question like propellant pressure is greater, lesser or equal to atmospheric pressure. So it is greater than atmospheric pressure. Now, let's see propellants in depth. So it is a heart of aerosol package. Heart is something very important. Like we always say, like heart is the determines, like it is the important part. So the heart of the aerosol package is propellant. It supply the necessary force to expel the product, and it also act as a solvent and diluent. Next is classification. Compounds used as propellants can be classified into following. Remember these one, which comes under what category. So first is liquefied gases. So they are CFC and HCFC, chlorofluorocarbon and hydrochlorofluorocarbon. So basically remember these are non-flammable. Several of the fluorinated hydrocarbons have an expansion ratio of about 240. What do you mean by expansion ratio? For example, when it is in liquefied state, if it requires 1 ml of 1 cubic centimeter of area, then when it will convert into gas, it will expand 340 times. Means if here it is requiring 1 cc, then here it will require 340 cc. That means expansion ratio is very high. That is 340. I'm sorry, 240. But dimethyl ether has a value over 350. That means dimethyl ether, when it is in liquid form, it requires, for example, 1 cc. Then similarly, when it is converted into gas, it will require 350 cc. So that much time it will expand. This is nothing but expansion ratio. Next is compressed gases. Compressed gases expand only to the extent of 3 to 10 times the original value. Compressed gases generally do not expand much. That is 3 to 10 times of the original volume. Next type is hydrofluorocarbon, HFC, and hydrofluoroalkane, that is HFA. Hydrocarbon ethers. Now what are the examples of compressed gases? So soluble is carbon dioxide, and non-soluble compressed gases are compressed air and nitrogen. Remember this one, carbon dioxide is soluble and compressed air and nitrogen are non-soluble. Now this is also very important, which propellants are for oral and inhalation and which are for the topical one. Since we have seen the aerosols, they can be taken by as a topical one, oral, or through face mask. So there has to be some different categories for topical and oral and inhalation. So first see about the oral and inhalation. So fluorinated hydrocarbons. So first is fluorinated hydrocarbons. That means fluorine will be there. So trichloromonofluoromethane. Trichloromonofluoromethane. Next is difluoromethane and dichlorotetrafluoroethane. We are going to see its nomenclature also. So these are the example of fluorinated hydrocarbons which are used in the oral and inhalational purpose. Next is topical. For the topical, hydrocarbons. Simple your hydrocarbons like propane, butane, and isobutane. Butane and isobutane are isomers of each other. Next is compressed gases. They are also used for topical aerosol like nitrous oxide, nitrogen, and carbon dioxide. Carbon dioxide is soluble one and nitrogen is non-soluble or insoluble. So remember what are used for oral and inhalation and what are the propellants used for the topical one. Now very important, let's see towards the nomenclature of propellants. So basically nomenclature of propellants is designated by 3 digits. Okay. So first digit, then second digit, and the third digit. For this, you should know how to evaluate or how to calculate the molecular formula of the compound. There are few propellants, and they may ask you question regarding like what is propellant 011 or like that they will give and you will have to identify. So see, it is designated by 3 digits. Simply what you will have to do, whatever molecular formula they will give, or if they give name, you will have to calculate the molecular formula of the propellant and then calculate the number of carbon, hydrogen, fluorine, like that. We will see the examples also. Now it is designated by 3 digit. Now first digit is number of carbon minus 1. Means whatever the total number of carbons are there, you have to subtract from that 1. For example, methane. We all know that methane is having 1 carbon. So the first digit will be number of carbon minus 1. Now in this case, number of carbon is 1. So 1 minus 1, it will be 0. So your first digit will be 0 because number of carbons, number of total carbon minus 1. In case of methane, only 1 carbon, so 1 minus 1, 0. Next is number of hydrogen plus 1. Number of hydrogen plus 1. Now we all know in methane how many hydrogen are there. So methane formula is CH4. We all know 4 hydrogen atoms are present in methane. What is our rule? Hydrogen plus 1. So you have to do 4 plus 1. So that becomes your 5. That becomes your 5. Number of fluorine atoms. How many fluorine are there? No fluorine atoms. So it will be 0. So this is for the methane. Now we will see exactly what is the how this is applied to the propellants. Now let's see the examples. Now see first example. Now first see example trichloromonofluoromethane. Trichloromonofluoromethane. Now we all know methane is nothing but CH4. That means one carbon. Trichloro means three chlorine atoms. Cl, Cl and Cl. And monofluoro means one fluorine atom. So this is the formula for the first one. Here you can see CCl3F. Here you can see CCl3F. Now you have to represent by 3 digits. Now according to our rule, number of carbon minus 1. Number of carbon minus 1. How many carbon atoms are present? 1 carbon. So 1 minus 1, it will be 0. Now second is number of hydrogen plus 1. Number of hydrogen plus 1. How many hydrogens are present? So there is no single hydrogen. So 0. 0 plus 1. So it will be 1. Third is number of fluorine atoms. How many fluorine atoms are present? 1 fluorine atom. So it will be 1. So the numerical designation will be 0, 1, 1. So here you can see the numerical designation is 11. Understood this one? Now let's see the second example. Dichloro-difluoromethane. Dichloro-difluoromethane. Now in this also, how many carbon atom? 1. So 1 minus 1, it will be 0. First will be 0. Afterwards, how many hydrogen? There is no hydrogen. So 0 plus 1. So 1. And how many fluorine atoms? 2 fluorine atoms. So it will be 2. So it will be 0, 1, 2. That is 12. Next is dichlorotetrafluoroethane. Dichlorotetrafluoroethane. Now ethane means 2 carbon. So this is first carbon. This is second carbon. Dichloro. So this is first chlorine and this is the second chlorine. Tetrafluoro. So 4 fluorine atoms. 1, 2, 3, 4. So this is the formula. So in this, how many carbon atoms are there? 2 carbon atoms. So it will be 2 minus 1. So it will be 1. And how many hydrogen atoms? Again, no hydrogen atoms are present. So it will be 0 plus 1. So it will be 1. And how many fluorine atoms? Tetrafluoro. The name itself suggests. So it will be 4 fluorine atoms. 4 fluorine atoms. Similarly for difluoroethane. Difluoro and this is a ethane. So number of carbon 2. So 2 minus 1, 1. Number of hydrogen 3 plus 1, here it is 4. 4 plus 1. According to our rule, 4 plus 1, 5. So 5 and 2. 2 fluorine atoms, so 2. So, and this A indicates the isomerism. The A indicates the isomerism. Now next is tetrafluoroethane. So if you calculate, you will get 134 for this one. Heptafluoropropane. Now it is hepta. Propane means 3 carbon. 3 carbon minus 1, that is 2. So it will come number of carbon 2. How many hydrogens are present? So in this case, single hydrogen is present. So it will be 1 plus 1 according to our rule. So it will be 2. And heptafluoropropane. Heptafluoro means 7. Hepta indicates 7. So it will be 2 to 7. So it is this numerical designation is for chlorofluorocarbons and hydrochlorofluorocarbons. From next you have to remember butane. Butane is A17. Butane is A17. Isobutane is A31 and propane is A108. So these 3 you have to remember. For the other ones, if you remember the rule, you can solve the numerical designation of these propellants. Now calculation of the vapor pressure of propellants. Now basically there are 2 laws, Raoult's law and the Dalton's law. So according to Raoult's law, partial vapor pressure of propellant in the mixture is calculated by Raoult's law. So Raoult's law is for the partial vapor pressure. Raoult's law is for the partial vapor pressure. A solution is said to be ideal when it follows the Raoult's law. So it states that the vapor pressure of mixture of propellants is simply the sum of their partial vapor pressure, that is P1 plus P2. So P1 is the partial vapor pressure of first propellant, P2 is the partial vapor pressure of the second propellant. So this is according to the Raoult's law. Next is Dalton's law. Dalton's law is directly about the vapor pressure. See, both are telling about the pressure only, the addition of the pressure. Difference is Raoult's law is about the partial vapor pressure, whereas Dalton's law is about the vapor pressure of mixture of propellants, and it is calculated as total pressure in any system is equal to sum of individual or partial pressure of the various compounds. So this is according to Dalton's law. Next is containers of aerosol package. Now we have discussed that inside the container the pressure is little bit high as compared to atmospheric pressure. So the containers should able to withstand that pressure. It should able to withstand the pressure. Now how much is the pressure? So containers must withstand pressure as high as 140 to 180 psig per square inch gauze at 130 Fahrenheit. This is very important. Containers should withstand 140 to 180 psig at 130 Fahrenheit. So what are the containers that can withstand these these pressure are, first is in metal. In the metal, there are tin plated steel, side seam, two piece or drawn and tin free steel. Second is aluminium. For you might have seen for the creams, ointments, greater resistance of corrosion. This has greater resistance. So two piece and one piece. So stainless steel, this is having higher cost and it is used for the inhalation purpose. So metals are there. Next is glass. Now glass, you know, if you give little bit of pressure there are chances like it will get rupture or it will be broken down. So the pressure for the gas will be different and pressure for the other containers, metal containers, are different. Okay, so in case of glass there are two types, uncoated glass and plastic coated glass. Okay, now see, tin plate containers. Tin plate containers are from Soundronic System, American Can Company, Crown, Cork and Seal, and the Southern Can Company. So these are the companies, and the Conovel System, which is a Continental Can Company. Organic coating can also be added to the finished container. So this is the description of these tin plate containers. Aluminium container. So aluminium container, it is corroded by pure water and ethanol. Remember this one, aluminium containers are corroded by pure water and ethanol. Ethanol and propellant 11 in an aluminium container produce corrosive products. So this is important. Ethanol and propellant 11. We have already seen the nomenclature. Next is stainless steel container. So it is used for inhalational aerosols. It is used for inhalation, stainless steel. No internal organic coating is required because this is a alloy. Stainless steel is a alloy. So no internal organic coating is required. Next is glass container. Next is glass container. So it is available with or without plastic coating. So as we discussed, glass will have different pressure to withstand unlike the other metal containers. So it is 25 psig, not more than 25 psig. So the pressure is not more than 25 psig and the propellant should not be more than 15%. So these are the limits for the glass container. Pressure is not more than 25 psig and the propellant should not be more than 15%. So remember these 2 points. Now valves. Valves are responsible for the delivery of the product in the desired form. This is important. It is responsible for delivery of the product in the desired form. So basically there are two types. Continuous spray valve, which is used with topical aerosols. continuous spray valve, which is used for the topical aerosols. Next is metering valve, which is used to disperse potent medicament, We have already discussed about metering valves, meter dose inhaler. So for the potent medication, which will dispense 50 to 150 mg, and its variation will be plus minus 10% of liquid at one time for nasal and respiratory airways. Now see, these are the different components, its function and what it is made up of. This is important. Now first is ferrule. We will see in, yeah. So this is the aerosol bottle valve assembly. So first is this ferrule, then this is stem. Stem will connect ferrule with the valve seat. Then this is a valve body, mounting gasket and the dip tube. This tube will go inside the container till the bottom. So first see ferrule or mounting cap. It is the topmost part. So it is used to attach valve properly to the container. So it is tin plated steel, aluminium with a single or double epoxy or vinyl coating. Remember which coating is given to ferrule. So epoxy or vinyl coating is given. Epoxy or vinyl coating. Next is valve body or housing. Valve body or housing. So it produces a fine spray and prevent valve choking. Valve body, it will produce a fine spray and it produces a valve choking. So opening is 0.013 to 0.080 inches. Very important, it is made up of nylon or delrin. This third column is important. So nylon or delrin, it is made up of. Valve body, it is made up of nylon or delrin. Next is stem. It connects the valve to actuator. It provides entry and exit port to the metering chamber to permit filling and discharge of meter dose respectively. It is also made up of nylon, delrin, brass or stainless steel. So this is stem is made up of these different types of materials, that is nylon, delrin, brass and stainless steel. Next is gasket. It is a seal between a valve and container. It is a seal between valve and container. Very important. Gasket, it is made up of 𝑏𝑢𝑛𝑎 and neoprene rubber. 𝑏𝑢𝑛𝑎 and neoprene rubber. Gasket, it is made up of 𝑏𝑢𝑛𝑎 and neoprene rubber. Next is spring. It holds spring because whenever you will press the nozzle, it will come above. Otherwise, it will not set. It will settle at the bottom only. So it should come back to the original place. So it holds the gasket in place when the actuator is depressed and released. That pressing is nothing but depression and release. It returns the valve in its closed position. So it is spring, it is made up of stainless steel. Dip tube, the tube will go to the bottom. It inside diameter ranges from 0.05 to 0.195. It is made up of polyethylene or polypropylene. Remember the dip tube, it is made up of polyethylene or polypropylene. Next is actuator. So to ensure that the product is delivered in the proper and desired form. So we have to ensure that it has to be delivered in the proper and the desired form, especially the design button or actuator when it is fitted to the valve system. So based on the material, there are different actuators. For example, spray actuators we are using for local anesthetic or antiseptic. So those are spray actuators. Foam actuators. So you might have seen the foam will require some more space. So these actuators will have some larger space. So large orifice semi-solid product. You might have seen for your shaving creams also the foam one, or face wash also, foaming face wash. So they have some little bigger orifice. Solid stream actuators. So semi-solid products like ointment. Special actuators for throat, nose, eyes and vaginal tract are used. It also allows for ease of opening and closing of the valve and is an integral part of almost every aerosol package. So this we have already seen. Ferrule, this is a stem, valve seat body, and this is a mounting gasket and a dip tube. So remember, gasket, it is made up of 𝑏𝑢𝑛𝑎 and neoprene rubber. Dip tube, it is made up of polyethylene or polypropylene. Now types of aerosol system. So depending upon the nature of different, like it is made up of solution, suspension, like that, there are different types of aerosol system. So first is three-phase system. Now we have already seen what is three-phase and what is two-phase. Three-phase means propellant, water phase and the vapor phase. So propellant and water are not miscible. If they are miscible means that will be a two-phase system. So propellant and water, we all know propellant it is non-aqueous. So it is a water immiscible. Next is co-solvents or surfactant. They are used to stabilize the propellant in water. Co-solvents or surfactants, they are used to stabilize the propellant in water. Next is solution system. So it is a two-phase system, no co-solvents. If active ingredient is soluble in propellant, then co-solvent is not required. So co-solvents are added if drug is insoluble in propellant. If drug is not soluble in the propellant, because propellant itself acts as a solvent, we have already seen. If it is not getting dissolved, then we are adding some co-solvents. Now suspension or dispersion system. This is also a three-phase system. Remember, water-based system, three-phase system. Solution, it is two-phase. Suspension or dispersion, also three-phase. They are difficult to formulate as compared to solution because they exhibit cracking, agglomeration. So these are the disadvantages in suspension. Next is foam system. So it consists of active ingredient, aqueous, non-aqueous vehicle, then surfactant, propellant to produce a stable foam. The liquefied propellant is emulsified and it is generally found in the internal phase. So these are types of aerosol system. Now we will see the manufacturing of aerosols. So very first is cold filling apparatus. So this method is not used to fill hydrocarbon. So the aerosols which are prepared by hydrocarbon, this method is generally not useful because it can be explosive. Both product and propellant must be, now product concentrate we have seen and the propellant, so it should be cooled at -30 to -40 degrees Celsius because to liquefy the propellant gas, propellant is present in the gaseous state. To liquefy that we have to cool down at -30 to -40 degrees Celsius. Cooling system may be refrigeration or dry ice. Dry ice is also known as solid CO2. Remember, dry ice, it is also known as solid CO2. After chilling, the product concentrate filled into cold aerosol container and liquefied gas is added. Afterwards, it is filled into the cold aerosol container and the liquefied gas is added. Heavy vapor of cold liquid propellant displaces the air in the container. So sufficient propellant is added, valve assembly is inserted and crimped, means they are positioned into their place. So this was about the cold filling apparatus. Next is pressure apparatus. So in which the product concentrate is placed into the container and valve assembly is inserted and crimped into the place. Now the liquefied gas under pressure is metered into valve stem from the pressure burette. After filling, the pressure is given under a pressure, it is metered. So the desired amount of propellant is allowed to enter the container under its vapor pressure. So the pressure in the container equal in the burette, the propellant stop flowing. Afterwards, when the pressure becomes equal, the propellant will stop flowing. Additional propellant may be added by increasing the pressure through the use of compressed gas. Whenever the pressure is equal, the propellant flow will stop. If you want to add more propellant depending upon the dosage form, depending upon the requirement, then the pressure can be increased so that maximum propellant will go inside the container. So this is the, since this is based on the pressure, it is known as pressure apparatus. Next is compressed gas filling apparatus. For filling aerosols with compressed gases, the concentrate is placed in the container. Concentrate means product concentrate, which is a mixture of active ingredient and other excipients. So the valve is crimped into the place and the air is evacuated. Air is removed by the vacuum pump. So the filling is inserted into the valve opening. The valve is depressed and the gas is allowed to flow into the container. When the pressure within the container is equal to the delivery pressure, again the gas flow will stop and the aerosol valve is restored to the closed position. So this was about the compressed gas filling apparatus. Now finished product specification. Now the first is flammability and combustibility. We all know that we are going to see evaluation parameters. So first is flash point. Very important, what is the apparatus used for this flash point? So first is standard tag open cup apparatus. Very important, standard tag open cup apparatus is used to study the flash point. So first is aerosol products chilled at minus 25 degree Fahrenheit and it is transferred to the apparatus, to this apparatus. The test liquid is allowed to increase slowly in temperature. First, the aerosol product, it is cooled down at minus 25 degree Fahrenheit and the aerosol product is allowed to increase the temperature. The temperature at which the vapors will ignite, it is known as flash point. For example, if it ignites at 40 degrees Celsius, then 40 degrees Celsius is the flash point of that aerosol. So remember at what temperature it is cooled and what is the apparatus used. Next is flame projection. Till what distance the flame is going after getting ignited, that is nothing but flame projection. So this test indicates the effect of an aerosol formulation on the extension of an open flame. For example, already one flame is there. If you are spraying your aerosol, till what distance that flame is covering, that is nothing but flame projection. So the product is sprayed for about 4 seconds. Remember this also, for about only 4 seconds you have to spray into the flame. Depending on the nature of formulation, the flame is extended. It will extend. So the exact length is measured with a ruler. Ruler will already be kept here like this. For example, here it is flame. If you spray like this, if it goes 2 centimeter or 3 centimeter like that, then it is calculated. So depending upon the ignition, it will show the flame projection nature. Next is physico-chemical characteristics. Physico-chemical characteristics. So vapor pressure. Vapor pressure is measured by pressure gauge instrument. Next is density. Density is measured by, remember, hydrometer or pycnometer. Next is moisture content, very well-known procedure, that is Karl-Fischer method using gas chromatography. So this is a moisture content. Next is identification of propellants. So by gas chromatography and IR spectrophotometry. So this will give you what kind of propellants or mixture of propellants are present in your aerosol package. Next is concentration propellant ratio. So how much amount of API and propellant ratio is present. So aerosol valve discharge rate. So this is determined by taking an aerosol product of known weight and discharging the contents for a given period of time using standard apparatus. So how much it is discharging from the container, that is calculated. So that is nothing but aerosol valve discharge ratio, discharge rate. Net content. So the teared cans that have been placed onto the filling line are reweighed and the difference in the weight is equal to the net weight. Empty cans, you will tear the weight and you will take the weight of your can. So you will come to know the net weight. What we have seen previously for the capsule is also the same. What net weight means, what is the actual weight inside the container. So the teared cans you will weigh and then afterwards this can. So the difference will give you the net weight. Next is foam stability. The lifespan. Foam stability means to what extent the foam is remaining. So it can range from few seconds to 1 hour also or more depending upon the formulation. So if it is for few seconds, then it is known as quick breaking foams. It is known as quick breaking because that disappears. Their lifespan is also very less. Next is, for this, rotational viscometer is used. Next is particle size distribution. This is also very important, which apparatus is used for particle size determination. So cascade impactor and light scatter decay method, this is used and the range is from 0.1 to 30 micrometer. Remember this one, 0.1 to 30 micrometer. And aerosol dynamic particle size. The particle size is known as aerosol dynamic particle size, that is APS. So thank you, students. This was all about the aerosol, right, from its mechanism to components and propellants. So thank you so much. We'll see the next chapter in the upcoming sessions. Thank you.